patata, 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 doo doo. Tech magnet. Tech magnet. Tech magnet.
So in terms of our unit on magnetism and electricity, electromagnetism, it's part of nature. They're two sides of the same coin. You can't have one without the other. When you have an electric current flowing, you generate a magnetic field. What was the key thing? A lot of weird math, but the two big ideas. How do you get an electric current from a magnetic field? You just have a magnet sitting there? No, it's got to what? It's got to change. You have to have a changing magnetic field, and you generate an opposing induced field, exactly, to balance out the energy there. So the electric current that's induced creates an opposing magnetic field to conserve energy. Another thing that you got to learn then is, if you had to add another keyword in, opposing, changing, and then the third thing I would add in is perpendicular, sideways. It's kind of weird. And the analogy is kind of like this, that if you want to push an electric charge, say this is like an electron with a magnet, if I take a big old bar magnet, whatever, up to it, I can't actually push it directly. It won't move in the same direction. It'll end up going sideways. It's like weird, but that's just how it works in nature. I got my little chair here I'm trying to push, and if this was an electron and I'm a magnet and I'm trying to push on it, it'd be like I'm trying to push on the chair and then it starts moving like sideways. Like, woo, it's kind of weird. But that's what happens in nature there. So there are 3 right-hand rules we're going to use. There's a whole bunch of variations, and some people like to come up with specific rules for a specific situation, like a left-hand rule. I like to keep it simple to try to help understand the basic ideas. So the first one is called the grip rule right here, where if you have a current flowing through a wire, you guys remember what the symbol I stands for? I stands for what? I is for electric current measured in amps. You take your thumb for your right hand, you point it in the direction of the current, and then your fingers curl in the direction of the magnetic field, B. And notice that the magnetic field is perpendicular to the wire. You see that? So magnetic field lines will flow in concentric circles perpendicular to the wire. Why is that useful? Because in real life, things happen in 3 dimensions, and you need to know which way the fields and forces are working. Most of us activate the power locks, lower the window. But if you're designing the car, you don't want like the doors to unlock when you want it to lock, or the locks to push sideways and pop your door apart. It doesn't make any sense. So understanding these basic fields and directions and forces is important. So one way to kind of notate things in 3D, we can do what's called the X and dot notation. So if you think of like an arrow flying through the air, like this, I'll just sketch this off to the side. If I look at it head on, then it would be like a dot, like the tip of the arrow is flying in your face. This is coming out of the page because we're trying to draw in 3D. And then if you think of an arrow flying into the page and you look at the tail feathers, that would be like an X, okay? Like the tail feathers going into the page. So let's look at it this way. What if I had the current, this wire, flowing out of the page towards you? Then which way would the field flow, if you think about it? So if I take this wire and I tilt it so that I is coming out of the page, then let's do the right-hand rule, right? If the current's flowing at you, then the magnetic field's going to go which way? Clockwise or counterclockwise? It's going counterclockwise, exactly. And then let's say I want to get the magnetic field now to go clockwise. What would I do then? All I would do is I would have the current go which way now if I want to go clockwise? Have it go what? Into the page, right? If they reverse the current so that now I goes into the page, the electric current. So if you're like, you know, designing a motor and you want to be able to reverse it, if you reverse the direction of the electric current and apply the right-hand rule, now the magnetic field will flow clockwise. You see that? In 3D there. That's the first right-hand rule. It's called the grip rule, like you're grabbing onto a wire or you're climbing a fire pole.